Hello, it's time to play some dominoes. Let's try pips. We'll start with the easy puzzle. Let's start solving. Okay, 12 needs two sixes, and one of the sixes connects to a 2, so that goes in immediately. The other 6 goes here. Now our only remaining 1 goes into the 1. That's fine. We have an equivalence made up of 2 of the same dominoes, so that's a 3, 2 of the same halves. Less than 2 can only be the 0, so that goes there. The inequivalence means we avoid the 2 there, and that's that. That was a very straightforward, easy puzzle. Let's try the medium. Okay, so we need to make a 4 out of, we don't have two 2s, so it'll have to be a 1 and a 3. And that will go into a 2. Oh no, no, 4 doesn't have to be, sorry, it could be a 4 and a 0. Yeah, it could be this, and then the 0 would go into a 2. Then we'd need another 0 out of the 2, which seems very plausible. We also have a 1 going into a non-equivalence region and a greater than 4 going into that same region. Well, we only have 1 greater than 4, so that's where I should have started. That goes there. That means the 1, 3 can't point in because we break the non-equivalence, which means, well, it doesn't really mean anything yet. But it means we can't put the 3, we can't put the 1 up, we can't put this domino up here. So the only place this domino must be in the central column somehow. So it could go down. No, it couldn't go down into that. Sorry, I meant to put it. No, it couldn't go this way either. Sorry. It could go this way, or it could be lower than that. This is as high as it could go. And this seems plausible, actually. This puzzle might have more than one way to solve it. If we put the 4 here, we'd have a 0, 1, 1, 0. No, that wouldn't work, actually, because we still need a 1 for the 1 region. So we cannot make the 2 out of 2 1s. We cannot do that. So what does that tell us? I think it tells us that this goes here, because if we use this to make the 4, we'd have a problem with 1s. So let's see. That means this would need to be 3 and 1. Yeah, this will work. There might be more than one way to do this, though. Yeah, that's fine. I'm not sure that was the only possibility, but it worked. So we'll try the hard one now. Okay, big grid. Sort of tree. It's making a tree there. All right, the 12 needs 2 6s. The 0 needs a 0. Those are all forced. We need an equivalence region of size 4 with a double running up the middle of it. So what could that be? It could be, what do we have doubles of? We have double 5, double 3, and each of those has enough additional cells. We have a double 0, but we don't have enough total zeros, so we can't do that. So it's 5 or 3 or nothing else. Okay, does it work with the 5s? If we put a double 5 in here, could we connect 5s to less than 3 and less than 2? We have a less than 3 here, but I don't think we have a less than 2. So it's not 5s. Oh, we have 1s as well. I didn't see that. So the 1s, could the 1s connect to those things? We have a 1, 0 and a 1, 2. Yeah, so it's either 1s or 3s. What about the 3s? 3s, I don't think that works, actually. No, we have a 3, 1, but we need an additional less than 3. Oh, no, we do. We have 3, 2 and 3, 1. That does work. Okay, so it's 3s or 1s down there, but not 5s. What about the 6s for the 12? We have 2 6s and they're individual. Oh, okay, this is where we start, because one of the 6s needs to connect to the less than 4, and there's only one possibility for that. The other 6 could go straight into the 4. Do we have any other 4s? Yeah, we don't know that that's how that works. Let's go back to 1s, actually, because we have a 1 here, and we'll need another 1 for the 1 region. So if we did have 1s down at the bottom, we would need at least 6 of them in total. Do we have that many? 1, 2, 3. No, we don't. Okay, I think that means it needs to be 3s. Oops. And then the 3, 4 doesn't go down there, so we have a 3, 1 that goes in the less than 2, and a 3, 2 that goes in the less than 3. Okay, that's fine. So now we need a 4 connected to a less than 3. And there's only one candidate for that. So that goes there. So now the other 6 points up. That's forced. Now the 1 points into a 1. So the 1 will have to connect to a 0 or a 1. We do have both of those options. And we do need to use one of the zeros here as well. And actually, the 0 must point down into the 1. So actually, these are going to be forced then, I think. Because we need, well, we could have this double 0 here, and then we would need double 1, or we could have 0, 1 here, and then we need another 0, 1, which we don't have. So I think it does actually need to be the double 0. Wait. No, we do have a double 1. If that went there, oh no, we need another 0, 1 is what I said. Sorry, so that's, yeah, so I think this is correct. I think we do put a double 0 there, then we need a 1, a double 1. Okay, I think that's correct. Okay, now we have a 4-sized equivalence region. Well, that will be our 5s now. Our 4 5s will go into that. And one of them is connected to a greater than 3, which will be this 4, because we can't waste our double 5, which now must go here. And then we've got 5s pointing into this 3 region, so we'll finish the 3 region with a 1. We have 2 possibilities for that at the minute, but we need to fill our single 4, which goes that way. Now the 3 needs a 0 to not break. And this is the last domino, and it fits. And there it is. All right. So yeah, that felt completely logical. That felt like a good solid solve. And that was all 3 difficulty levels. Those were the pips. All right. Back tomorrow. Bye for now.